Okay, cool. So here we go again. Thanks for sticking around. Our next speaker is Ori Plonsky from the Technion. And Ori is not a computer scientist. He's actually, I don't know you're like a really different construction of your department. So yeah, what would you call your field?
I'm actually in behavioral science. I mean the data and decision sciences.
Yeah, that's like, we don't have anything like that, although I think it's pretty cool that a data and decision sciences faculty take inspiration from that. But Ori is one of the real leading people in what is becoming a growing research area. We just had a workshop in NeurIPS on behavioral machine learning, which I think was the sort of realization as a room packed with like 150 people of something that Ori's been taking the lead on for a long time, which is really bringing a kind of modeling, machine learning kind of viewpoint to the problem of thinking about how real people in the world behave, rather than, in economics, kind of in the 50s, we had this really axiomatic view of how it is that people make decisions and act, which has somehow managed to really last in economics to this day. And in the rest of computer science, we've sort of left this very logical axiomatic viewpoint behind and replaced it with data. That change has been much slower in coming in kind of economics and the social sciences, but Ori's really been at the sort of thin tip of the spear, sort of bringing that change about. So I think this is a really timely thing. I'm really glad you can have you here today. So welcome, Ori.
Thanks a lot. Thank you very much for this very, very too kind, generous introduction. But it definitely set me up for my first slide. So behavioral economics. So as Kevin was saying, I would say I'm in behavioral science. I'm a behavioral economist. I actually have a bachelor in engineering, but a PhD in behavioral science. And I'm trying to bridge these two gaps together. And I'm going to start with a quote by Herb Simon. Hope you know who Herb Simon was. Extremely important person across fields. And he was saying, the phrase behavioral economics appears to be a pleonasm. What non-behavioral economics can we contrast with it? So economics is about people. What do we mean non-behavioral economics? He asks and answers. The answer is found in the specific assumptions about human behavior that are made in classical economic theory. And I'm not the person, and I guess this is not exactly the crowd to mention exactly what are these assumptions about human behavior, but in lack of a better word, let's call these assumptions rationality. Okay, so it's not a good word, but let's say that economics assumes, or neoclassical economics generally assumes rationality. Which brings us to a puzzle that Kevin nicely set up here. Neoclassical economic theory assumptions are clearly wrong. So we have thousands of papers with books. We see ourselves behave. Clearly, we are not rational. So why do they persist, these assumptions? And we can think of several answers to these questions, and at least a couple of these answers are pretty good, in my opinion. First of all, we might not care, because what we're looking for in economics in the specific case might be a normative prescription, what should be done, rather what people are doing, in which case maybe these assumptions are a good starting point. A second explanation might be that these are good first-order approximations of what people do. We don't know exactly how people behave in each individual context, but in general, if we just assume it's a first-order approximation that people are doing what's best for them, then in general, we might see behavior in markets, in the economy unfolds as our theory predicts. And if these are your answers, or economists' answers to these questions, to this question, then that's fine. But I've also heard economists answer a third way to this question, and that is we can't do better. We cannot do better than the neoclassical economics theory assumes. And this is because behavioral science is full of explanations of behavior, but very few predictions of behavior. So we have a lot of ways to look at the data and then explain why people behave the way they did. for example, not rationally in a certain case, but we don't have a good prediction of when they will behave irrationally, rationally, or in any kind of irrational way that we want, and why. So basically, we have a lot of contradicting behavioral phenomena. Just for an example that is nice from the financial markets, there's a phenomenon called equity premium puzzle. This equity premium puzzle in financial markets is the observation, empirical, historical observations, and it consists today that investors demand far too much high premium for investing in risky assets, in stocks, over riskless assets, bonds. So this implies very strong risk aversion. People do not like risks in investors in markets. In contrast, we also see in financial markets that investors have a general preference for individual stocks over index bonds. This implies actually risk-seeking because index bonds are more conservative, risky, but people still prefer the individual stocks, and we have investors both preferring to avoid risk and take too many risks. Now, this of course is contradicting, so behavioral science comes and explains these two different phenomena in two different ways. One explanation for the equity premium puzzle is, for example, loss aversion. I assume maybe you've heard of this term, the idea that people are dislike losses more than they like gains. This is why people demand a very high premium for risky assets. And people are risk-seeking because they are overconfident. They think that they know more than they do, and so they should invest in individual stocks. But of course, if we have an explanation, two different explanations, two different behavioral phenomena that explain two contradicting effects, then we don't have good predictions for how people really behave. Basically, behavior is not predictably irrational, and I want to claim that this is not the case. I want to claim that we can predict behavior, at least in a stylized task, which has been the basis for basically behavioral economics since the 1800s, maybe, mainly since the 1950s. For the past 80 years, we had hundreds of papers in behavioral science and economics researching this exact type of stylized task. Choice between risky lotteries. So this is one example of the task. Please choose between A and B. A gives 3 with certainty, you can think about it as dollars. $3 with certainty. B, 4 the probability, 0.8 or nothing. And we let people choose between these lotteries, and we see what they choose. And what I want to show today is that we now have a model that predicts behavior, or at least the average behavior of people in these types of tasks, extremely, extremely accurately. Now, why should we care about this type of task, except that it was the basis for all behavioral decision making, a lot of behavioral economics, a lot of microeconomics research? Well, we can think of applied from an applied perspective. Let's say we're policymakers, and what we want is to incentivize some desired behavior in the population. As one example, something that I was involved in the past, we want to decide, we want to pay people for not driving, leave their cars at home, okay, work from home or take public transportation or whatever. And we have some budgets from the government to actually pay people to do this. And now we can ask, okay, how do we allocate the budget? How do we decide on an incentive structure that would make as many people as possible to actually leave their car at home for a given budget? So we can ask the experts, the behavioral economists. Problem is that each behavioral economist might have a favorite behavioral phenomenon that they would say is important. For one would say we should use loss aversion. People are loss averse. They hate losses more than they like equal-sized gains. So what we should do, for example, is we should give them the money in the beginning of the month, and every day they go and use their car, we take some of it away. So they feel the loss, and that's why they would leave their car at home more than if we actually just pay them when they do it. Another would say, no, what we know from prospect theory, which is a very central theory and how people in behavioral economics, how people behave, is that we should use lotteries. I mean, if we just have $5 or $10 for each day that people leave their car at home, then it's not incentivizing enough. But if we tell them that each day that they leave their car at home, we give them a lottery ticket with a probability of 1 in 100 to get 100 times more. So, for example, $500,000 or $1,000, then they would adhere more. A third person would say, no, there's diminishing sensitivity. I won't go into that for lack of time. But in essence, there are many, many, many different behavioral tendencies that people exhibit. So what should we do? We might experiment, see what's best. So we actually are in collaboration with the government, can do a pilot experiment, actually randomly allocate treatments to people, to different groups of different treatments, and then we see what works best. Of course, one problem is that there are many possible treatments, but it's possible to actually have a pilot that experiments over many possible treatments. This has been done. This is an example paper from Nature a couple of years ago. It's called a mega study in behavioral science. What we do is we actually examine dozens and dozens of different treatments to see what works best. In this case, it was to get people to go to the gym more often. So this is possible. This has been done. Of course, it needs a lot of money for that. There's a lot of power, like Katie and their colleagues have. But then you get an answer. The problem is that what happens if suddenly the world changes? So you got an answer for how the world used to be. You don't have an answer for the new world. For example, the government might say, okay, we actually don't have this much money to pay people. Just cut the budget by half and now decide which incentive structure to use. Of course, this is a problem. Okay, so I should not, of course, it's simple to explain to this crowd. This is basically a prediction test. So we don't need to actually run an experiment and see what happens. What we have is a prediction test. We are asking what incentive mechanism will be most effective, or given an incentive mechanism, what will the population do? So we want to predict the population response, and how can we predict behavior? In behavioral science, we might ask behavioral scientists. The problem is that often behavioral scientists are not very good at prediction. This is actually a print screen from that paper I've shown you about mega studies. You don't have to read this, but each row here is actually one treatment, one behavioral treatment designed to make people go to the gym. The blue lines here is actually the effect. Okay, so this is 0 times that they went to the gym. This is 1/2 time that they went to the gym more in a week. So as you see, the effects are very small. Okay, but these are the effects we have in behavioral science. Nothing much more than that. The issue here is that the orange lines here are actually the predictions that expert behavioral scientists, behavioral economists gave for how this experiment will go through. So we see two things. We, behavioral scientists, wildly overestimate the behavioral effects. And second, there's zero correlation between what we predict will happen and what actually happens. At least in this case. Okay, so behavioral scientists, not the best idea maybe. So we can go to data scientists. This is what most of you probably do in many cases. Develop models that predict something. In this case, we want to predict behavior. In this case, we will have them all take as input the incentive mechanism and return prediction for how the population will behave. The problem is that often in behavioral science, we have too little data for developing predictive models. For example, if we want to predict how the population will respond to an incentive structure we impose on it so that they will leave their car at home, we might be able to get pilot data for 10, 15, 20 different treatments. But this is the observation that we have. So we can't really rely on data-driven approaches. So what should we do? Data scientists, behavioral scientists, in this paper we suggest using hybrid models. The hybrid models use behavioral theories to create engineered features. So we use behavioral theories to engineer features, behavioral theories to engineer features, and then we put them into a machine learning system. Now, a word about model evaluation in this case. I'm sure you know, but I'll stress this. Models that predict new treatments must only see the trained data while being developed. And therefore, they must be completely independent of the test data during model development. Unfortunately, this is often not the case also in machine learning. If you think about it, if we use a common data set, then we know what worked on that common data set because there are previous papers from this common data set that we know how they did on the validation or test. So we do have some knowledge of what works within this common frame data set. Also, if we develop our own data sets, we need to of course, rely on the integrity and naivety, maybe, of the researchers in order to do this properly. So the solution, as I'm sure also, again, you know, is centralized evaluation mechanisms, for example, CAIDA. Okay, so we actually do mock competitions. Specifically, this one is not in Kaggle, but we do hold model competitions for this prediction task, given new choice problems, all decisions on the risk and uncertainty, choice between lotteries. We need to predict the distribution of aggregate choice. So we collect the trained data. That is, we collect data on how people behave in some choice problems. We published it. We invite other researchers to submit better models than the baseline models that we propose. Then we collect the test data and we evaluate all the submitted models on the test data. Okay, so we have a bunch of these competitions in the past. I'll talk about one of them. CPC 18. Again, it's the point is to predict how people choose between two choice options that are described this way. The space of problems in which we take these tasks form is much more extensive than this very simple problem. In some cases, we hide the probabilities, so people don't know the probabilities. In some cases, we have up to 10 different outcomes here. In some cases, we have also feedback, so we let people choose between these options repeatedly over time and get feedback and see what they do, and then choose again. And in general, we assembled a space of choice tasks that is fairly representative of a lot of basic behavioral phenomena. So we actually have this space that captures, I think, 14 or 15 different fundamental behavioral phenomena, all of the phenomena that prospect theory, for example, captures, and many more of these. And so we have this distribution of tasks, and we randomly generated 270 tasks from this distribution, and then we ran it on people and see and collect the data. And before I'll tell you the results of the competition, a note about model accuracy. How do we measure accuracy in this task? Well, mean squared error. Okay, so we take mean squared error as our criterion. But since mean squared error is hard to interpret, it's only good for comparison between models, we also use another measure, which is a transformation of mean squared error, basically. This is a paper by some economists, important economists, Goodman and others, that suggested completeness. What is completeness? Completeness is basically the proportion of predictable variation in the data. This is what can be done. So completeness of 100% cannot be beaten. This is a perfect model. Okay, completeness of 100% means the prediction ability of a perfect model that knows everything there is to know about the population. It knows the parameter. Of course, the perfect model also does not have error of 0 because we test it not in comparison to the population parameter, but on the sample proportion. So we have a sample from the population, and we test the error based on that sample. So the thing to remember here is what is completeness of 100% is everything that can be done. So we had a nice turnout to this competition, 46 registered teams from 34 institutions, 16 countries. They spent a nice amount of work on this, and the winning submission is a model that we now call Beast GB, or Beast Gradient Boosting. It's a hybrid model submitted with this bunch, Roger, Peterson, Lachlan, Griffiths, and Russell. It's a hybrid model that uses both behavioral theories, this is the Beast part, and machine learning, this is the gradient boosting part, in order to predict behavior in new treatments. And the nice thing about it, it's 93% complete. So it predicts with very, very high accuracy how people behave in a new task within this domain. So what's the behavioral part? The behavioral part, Beast, is an existing strong behavioral theory for how people choose in these environments. It's a model, behavioral model that actually won an earlier choice prediction competition. It assumes people are sensitive to expected value and that they have several behavioral tendencies. So they are sensitive to a bunch of stuff that they see in the choice task, and this makes them choose a certain thing. For example, it's one of the assumptions that people assume the worst. So if they see some choice problem, for example, 3 with probability 1 or 4 with probability 0.8 or 0, they assume there's a small tendency to assume that I'm getting screwed over, that I'm going to get 0 if I bet here. Okay, then they're telling me that 0 is probability 0.2, it's not. It's going to be probability 1. So this is an example of a tendency that people have when they choose. Another tendency, an important one, is to prefer the option that minimizes probability of immediate regret. So people hate it when they choose something and they see that they could have gotten better had they chosen something different. The probability of that happening, so I'm not talking about long-term regret, but I'm talking about immediate regret. I choose something, I see that I could have done something better, this is regret. The probability of that happening is something people are very, very sensitive to. And this is actually something that we see they are very sensitive to and getting more and more sensitive to as more experience they get within the task. So the more I do the same thing again and again, the more I see that I couldn't gotten better had I chosen differently, the more I'm likely to choose the option that minimizes this probability. Okay. So what we do is we take so BGB basically what it does is it takes this theory, this Beast theory, and it decomposes it into its basic assumptions. So for example, if Beast is a theory that predicts that people are a little bit sensitive to the worst possible outcomes, they're a little bit pessimist, they think they're going to get screwed over, then one feature that we implement here is the difference between the worst possible outcomes. So we give the model an inductive bias that tells it what to look at. For example, what's the worst that could happen? If it's minimization of regrets, the difference between probabilities of regrets. In addition, BGB also includes a feature that is at the actual prediction of the behavioral model, the prediction itself. So this is what the model does. It predicts very, very nicely. But in any case, feature report. In any case, this is the SHAP values for the different features for the test set of the competition. And what you see here very clearly is that there is this one feature that is extremely important for this prediction, and this is the prediction of the behavioral model. So the behavioral model in itself is already quite good in prediction of behavior there, and therefore the feature is very, very useful, but there are other things. For example, these two are relevant to probability of regret. Okay, so we had this competition, we had this hybrid model that won it very nicely, and now it has two parts. It has the behavioral part, it has the machine learning part. We were asking, do you really need both the behavioral part and the machine learning part? We have two questions here. So the first question, are behavioral theories really necessary for good predictions? Maybe all we need is a good machine learning algorithm that learns from the data and outperforms this option. So we don't know, of course. Maybe we don't need behavioral theories. Maybe someone will come along and show us wrong, but we do know that none of the submissions to the competition were actually doing this. We're actually doing data-driven, pure data-driven methods. All of them use some behavioral features, and this is despite the fact that 16 of the researchers that were registered to the competition were AI researchers. So they were people that knew what they were doing in that respect. And the winners themselves are a group of AI researchers, and they said that before submitting this, we tried a massive high-parameter NLP for weeks with objectives, so not without behavioral features, without any behavioral logic, but we were strictly worse than the baseline models, so we could not do anything. Moreover, we lately tested whether fine-tuned LLMs could outperform me. They could not, but this is later. So how can that be? What's going on here? This is a prediction task. Why don't the data-driven methods work? The obvious question is that we have too small data. Maybe the data, we only can have 210 different observations to train on. Maybe the data is too small. Luckily, a couple of years after the competition, this paper came out. This is a paper published in Science. And what they did is they created a new data set called Choice 13K. And in that data set, they again used the same paradigm of choice between lotteries. This is a print screen from their paper. Choice between lotteries, again, 16th probability with certainty, or 1 or 44 or whatever. And here, the paradigm was similar, not identical. It used a different population, but more importantly, it was the largest data of risky choice ever collected. So now we have, this is a TSNE visualization, two-dimensional visualization of their data set. We have nearly 10,000 different choice tasks. Before we only had 210. So the 210 are actually in red here. Okay, the red dots. The black dots are actually the 10,000. The X's are historical data sets that were used in development of prosthetic theory. So we have a nice cover for the space here. And now finally we have a sufficient size data set in order for data-driven methods to outperform behavioral theories, or at least hybrid models. And this is again a print screen from their paper. What you can see here on the y-axis is the test set mean squared error, so lower is better. And on the x-axis, we have the percent of the training data used. So we can see also the sample efficiency for how well it does. And the purple here is actually a neural network unconstrained by behavioral theory in any way. So this is a data-driven, purely data-driven model. And it did best in their paper. This is already not a print screen from their paper. This is from our paper. The purple one is still that neural network from before, the same purple line. Now, what you can see here is that BeastGP outperforms this hybrid model that includes the behavioral theory, outperforms the pure data-driven method by 25% in mean squared error. Okay, again. And this is also true when we only train this hybrid model on 2% of the training data. So training the hybrid model on 2% of the training data already outperforms the data-driven methods that are trained on all 9,000 trained data problems. So behavioral theory can go a long way. One thing is that you can see a small difference, 2 lines here, small difference at the beginning. This a lighter line is actually for a model, the exact same model as the hybrid model that won the competition, except we took away the feature that gives it the prediction of the behavioral model. So what you can see is that when you give it the prediction of the behavioral model and you train it on small amounts of data, it helps. But later on, it learns not from the task, but it learns from the behavioral assumptions embedded in the engineered features, how these behavioral assumptions form together into one coherent model, and it predicts at the same level. Interestingly, Beast's prediction is still the most important in SHAP values. Okay, so this theory is still a highly useful thing to do. The second question is, do we really need machine learning? Maybe we just have this extremely powerful behavioral model, and all we do is get a little bit better by adding the machine learning on top of it. So it turns out that there are cases in which it can be extremely useful. And these cases, we think, are cases in which the behavioral theory that underlies the hybrid model is actually too rigid, too inflexible to capture new idiosyncratic context-dependent effects. So we took a third data set published in a third paper, this one mentioned Science. What they did is they took and assembled 19 different behavioral experiments. Each behavioral experiment run in a different place by different researchers in a different rollout in a different paper. And what they do is that they look at how different behavioral models, existing behavioral models from the literature, predict in this data set. It's a different problem. I won't go into too much detail why it's a little bit of different problem, but more importantly, it includes many different types of choice problems, a different data distribution of choice tasks. Again, this is the TSME of all the tasks that we actually use in this paper, so all three data sets. The red one is the CPC18, the gray ones are the choice 13K that I've just shown you, and the light blue ones are from this new data set. And you can see here, there's a large cluster of choice tasks. They're different. They are not the same as those that were used in the previous data sets. And the reason they are different is that they include tasks that are apparently very simple for humans to solve. What would you prefer, 100 with certainty, $100 with certainty, or $500 with probability 0.9? I mean, when I ask this, almost every time I get the answer, of course 500 probability 0.9. I mean, what's the deal? But interestingly, in this data, 50% chose the stupid option of 100 certainty. And the reason this is because these choice tasks were run in experiments. They were designed to make people choose odd things. So they were context-dependent, highly context-dependent behaviors. And these are the problems here. And when this is the case, the behavioral theory performs very poorly, because it assumes people are somewhat sensitive to expected values. People are not very stupid, just slightly stupid. So if they're not very stupid, they should choose the 500 probability 0.9, but this is not what happens, because there were context-dependent effects. So if we compare the performance of the different models, this is the behavioral theory, the Beast behavioral theory model, on the test set mean squared error, you see that it performs poorly in comparison with many different models. But when we add on top of it the machine learning, then it outperforms everything else with 95% completeness. So nearly all of the predictable variation in the data is captured once we add machine learning on top of the behavioral theory. And again, interestingly, even though this theory predicts very poorly, most important feature, again, the prediction of Beast. And the reason for this, we think, is that Beast, in fact, captures the variance across tasks in how people behave in these weird domains. What it doesn't capture is the large bias, and machine learning comes and corrects for this large bias. So we also get a lot of information from the behavioral theory and a lot of accuracy using the machine learning. Right. Now the most important, I think, or the nicest result that we have with BeastGPT, this hybrid model, is that it can generalize across domains. Specifically, it's very good at predicting behavior in new treatments when we train it within data sets. So we split a data set, train the test, and then we use the train to predict the test. It's very, very good. But can it generalize across new experiments? Nicely, that last data set, as I said, it took and assembled 15 or 19 different behavioral experiments. So what we do is, it's 15 actually. So what we do is we take these 15, we train on 14 of them, and we try to predict a 15th. So this is trying to predict a completely new population, new sample of people, in maybe a new software, different, of course, the same task, choice between libraries, but in a new domain, so to say. And here, BGP is not as good, it's 86%, but it's still much, much better than anything we've seen. But nicely, we also have a very, very strong benchmark to compare it to. Now, in these 15 different experiments, sometimes researchers in behavioral science, they have a tendency to use the same stimulus again and again. So different researchers writing different papers on different topics, they use the same choice task, the same choice between libraries. So in 31% of the choice tasks in our data were actually choice tasks that were repeated across experiments by different researchers, different samples of people, different software, but it's the same choice task. So what we can do if we have the behavioral people in one experiment, and we want to in the same task, and we want to predict the behavior of people in a new experiment in the same task, of course we can do direct empirical generalization. The new people in the new experiment will just behave the same as the old people in the old experiment did. So this is direct empirical generalization. Amazingly, our hybrid model actually beats this. It performs better than direct empirical generalization in predicting new experimental results. And this is by a margin, actually. And this is 92% complete. So basically what this means is that the average error of the model is smaller than the average sampling error in behavioral experiments. That's good prediction. Okay, so this is what we did so far. What's next? Now, is this hybrid approach only relevant in choice between lotteries, this domain, which might be important, but perhaps not very applied, because you use precise numerical information on outcomes and probabilities? What we're looking at next is a space of choice tasks in which, instead of precisely describing the option with numbers and with the probabilities and outcomes, we're going to describe the options with free text. So think about marketing ads, warning signals, warning signs, any textual information, for example, for drugs, whether side effects or what side effects there are, and so on. So in the real world, we keep on facing this textual information, and we need to choose whether to pick options based on textual information. So what we'll do is we will hold a new choice prediction competition. You are welcome to participate. And in this new choice prediction competition, we will ask people, researchers like you, like anyone who wants, to predict how people choose between these types of tasks. We already collected 1,800 different tasks of this sort. For example, this option is better for those who prefer avoiding larger losses to the concentration gains. And this one, there's more than even chance to come out ahead, yet the risk of a bigger loss is present. Now, this is the way this is presented to people in the lab, and we see how they choose based on this textual information, without them knowing behind the scenes there's actually, again, a lot. So this is actually the one description, possible description of minus 3 certainty. This is one possible description for 2 with probability 0.53 or minus 7. So how do people choose there? In our initial results, because before we hold the competition, we actually try to create a benchmark model. Our initial results suggest that the way people behave when they see this type of textual information problem is that they have these sorts of initial tendencies, propensities. The thing is that we don't understand these propensities, these tendencies like pessimism, before, or probability of regret before, we don't understand them well enough in this domain of choice between free texts. What appears to understand it better than us researchers, behavioral researchers? LLMs. So LLMs, fine-tuned to this task, were actually the best that we could do so far, initially, to predict how people initially behave when they see this. Only this. So they see this, and we fine-tune an LLM to this task, and then this is the best we can do. However, we also give people, after they see this for the first time, if they choose, we also give them feedback. And we let them choose from experience again with these two tests in front of their eyes. But then they also see what they get from choosing each option. And here what we see is we actually do need a behavioral theory. We do need a behavioral theory of how people learn from feedback, because this outperforms the fine-tuned LLMs. So initial results suggest that, at least initially, it's very hard to predict these context-dependent, very, very idiosyncratic effects of how people behave when they first see a task. But when we start getting people to choose repeatedly with feedback, interact with the system, then we have a very good understanding of how they learn. By the way, this is not learning like reinforcement learning. This is not learning to maximize. It's a different model that we can discuss offline, but it's very similar to how BEAST, that behavioral theory before, learns. Yeah, summarize. So we have a specific hybrid model, BEAST-GP, but in general, we think that hybrid models that integrate behavioral insights and machine learning can be very useful. This specific model in 3 large data sets with over 11,000 tasks outperforms everything that we've tried it against, and it basically almost solves the task. It predicts at 95, 96% predictable variation. It captures 95, 96% predictable variation in data. Now, on one hand, we have behavioral features that seem to be necessary, even with relatively large data. I mean, 10,000 problems might be a joke to some of you, but 10,000 problems, huge data in behavioral science. Even then, we still need behavioral features. On the other hand, when we see context-dependent idiosyncrasies, we have machine learning models that actually come and correct for the bias of the behavioral theory. And then we can actually achieve even domain generalization at levels better than direct empirical generalization. And we think that while AI and ML can help predict initial people's behavior, because it's very idiosyncratic context dependent, once people start engaging with the system repeatedly and seeing how it behaves, then we have behavioral theories that predict it fairly well, much better than economists might expect. So behavior is kind of predictably irrational. Okay, thank you very much.
I'm curious about the generalizability of your results beyond a lab setting, since it sounds like the experiments have all been the case of you sit people down in a lab and ask 2 choices, but would this also apply to when they're actually given the 2 choices while not in a lab setting, while just scrolling on the internet or something? Do you have any thoughts on that?
Yeah, so an open question, of course, if you're going to see. So basically what I'm thinking that we need to, this is the first step for this. And the next step should be something more real world, but a little bit related to this choice between lotteries setting. So maybe, I don't know, a choice between investment portfolios, for example. So many times you come to the bank, you ask to help them to invest, and then they ask you a bunch of questions. What do you prefer, that your portfolio drops or portfolio drops with a small number of points or a large number of points, but then it has also this advantage. So basically, we know this questionnaire is based on something, probably not specifically on BEAST, but maybe across the theory, maybe on rational choice. I think that maybe we can start by trying that in the field, this GPU model in the field in these types of situations, but I don't know, it's another question.
Have you had any insights in trying to interpret the machine learning model on top of these to gradient boosting?
Right. We did try this, and of course, this is actually a second round review, so the reviewers are very this exact question: what do we learn? And it's very hard to interpret the differences between the machine learning and the component beyond the behavioral theory. The one thing we can say, for example, is in this data set, as I was saying, in this final data set, in which it is clear that what the machine learning adds is that it removes completely the dependence on expected values, and it makes the other tendencies much larger. Other than that, I'm not sure what happens, and this is something we definitely need to try. We're trying different XAI methods, but nothing seems to come up. Yes. Yeah.
Just one clarification question. You mentioned that the assumption about immediate regret.
Right.
So I'm quite intrigued. So can we have some examples?
Yeah. Sure. An example would be from real world would be if you're driving a car and you get a text message.
Okay.
Now you have two options: to look or not. Not looking has a high probability of regret. Okay, it's a high probability of regret. Of course, it's the right choice. On average, it's better not to look. But this is a very high probability of regret. Why? Because if you look, then, I don't know, 99.9999% of the times, nothing bad happens, and at least you get this little endorphin. Okay, I looked, something probably very boring happened, but at least it's better than not looking, which feels terrible. Okay, I'm missing something. And then once every 10,000 times you do this, you crash. Okay, so there's a very high regret on average of looking, but the probability of regret from not looking is much higher. So people actually learn in the direction of probability of regret. And of course, we see people looking at their phones all the time. But this is a real world example.
So it's mainly about you have to make some immediate action and you don't know the outcome of these two. So if you take long, you may very likely to regret for not taking.
Right.
Yeah. Okay. Right. Thanks.
Yeah.
Do you know that if people realize they're doing that, this has like a multi-agent setting to actually people actually assume other people are doing that?
Okay, thank you for this question. I actually have this paper right now that tries to answer this. And what we see is that with repeated interactions, people can exploit that tendency by other people. So we have an asymmetric gain, the game theory. So we have an asymmetric gain in which one case people actually have this opportunity to regret with high probability, and the other person needs to choose where they go, and they can exploit this tendency.
That's going one step further. Like, okay, exploit. I just want to think just in terms of like expectations, or like, let's say we're going to create one of those AI agent assistants to a person. Would they feel like that agent is performing more aligned with what they expect than if that agent was also doing this, minimizing probability every day, just because they themselves have that tendency? So
Yeah, excellent questions. The reason is that I have another paper that discusses this exact problem. Excellent paper. Excellent question. So what we show is that if we give advice of humans and advice of recommendations by humans, recommendations by AIs, and the AIs are optimal, but they have high probability of regret, people prefer the humans. And vice versa. If we give human advice and AIs, then what they do is they optimize for this objective function, minimize probability of regret, then people love doing that.
I wanted to ask about your domain generalization results.
Great question.
And it's so surprising, I'm kind of doubtful that it's true.
Right.
I mean, you claim that this was showing that these GPU does better than sampling error, but shouldn't the sampling error be reflected in your error bars here? It doesn't look like it's better. It looks. Like, I don't see why,
This is the,
like, you might.
this is not sampling error, so sampling error is within task. So the average with sampling error within task. And this is sampling error, this is not the sampling error, this is the error across tasks.
Oh, so it maybe would have been a good idea for you to, do bootstrap replication within.
This is bootstrap consciousness across tasks.
Oh, that's- I mean, it sounds like you're claiming there's a source of variation that you haven't drawn error bars for here. That is.
No, because what I'm trying to predict is the average behavior in the population.
Uh-huh.
This is what I'm trying to predict. I'm trying to predict the average behavior in the population. So there's no source of variation within this task because it's one number. What I'm saying is that this average behavior in the population comes from the average of many participants in the task. And this also has a sampling error, right? This has so okay.
Something you could bootstrap, right?
This is not what I'm trying to do. I'm not trying to predict individuals. I'm trying to predict the average behavior.
The average is going to change as you subset the individuals.
Right. Okay. Good.
But,
Okay.
But I mean, it just seems like you're actually looking at different experimental subjects, right? If I held out professional poker players and all of my experiments were with psychology undergraduates,
Right.
I would expect to generalize poorly because these behavioral parameters are not inherent facts about the world, they're facts about the specific people that will differ from one group of people to another. So to some extent, that effect must be present. These populations are not exactly the same as each other. So you would expect that to limit generalization on held out, treatments to some extent. And it's hard to see why Beast would do better than, given that it's trained only within the populations that it doesn't get to see anything about the new population, then it would do any better. Do you have any reason? It just seems.
Yeah. So
It seems like that ought to have been a lower bound. It makes me doubt what's going on statistically here.
okay. So again, the idea is that there is a population parameter for all of the population that ever can take this task in a lab setting. And then if we sample randomly in one experiment, and we sample randomly from the population in another experiment, we have so the target would be the new experiment. We have the sampling error from the population parameter in the first experiment. This, if we had an infinite number of participants in the first experiment, then we cannot beat this, of course, because then it would be the population parameter. But because it's not an infinite number of participants in the first experiment, it's somewhere between 30 and 150, depending on the experiment, then we can do better. We can actually predict with smaller error than this average sampling error taken from in the first experiment. I can actually simulate it. I have a code. I couldn't believe it at first as well. I simulated it. It's awesome.
Okay, so then I guess I refer to my previous question, which is that should show up in,
Right.
with the example generalization.
Got it. Sure.
Because so we agree asymptotically. Yes.
Asymptotically, yes. We cannot. Yes. Sure.
Thank you.
Thank you.
Last question for Ori.
Yeah.
How do you get people to leave their cars at home?
Okay, great question. So basically, if we assume this is something of a repeated interaction, right, with the environment, I do it again and again, day in, day out. So the best incentive structure, if people are, what they're doing is they are behaving so that they want to minimize probability of regret, is that you need basically just a simple fixed payment. So the best incentive structure, if you have $10 to pay each person each day, this is what you should do. You should pay them $10 each day. This is boring, but this is the result, because a lottery would not be good because I do the right thing, I leave the car at home, and most of the time, I get nothing. Loss aversion, not necessarily the best idea, because again, I do the right thing, and well, there we can argue if it's loss aversion can help or not. But basically, it's just the fixed incentive structure might be the best.
Okay, let's thank Ori again.
Thank you very much.